Hi, welcome to our ordinary differential equations. Today's topic is going to be about Cauchy Euler equations. Okay, by the way, if you are interested in the history of mathematics, these two individuals are very interesting personalities and extremely prolific in terms of their contribution to the mathematics. So Leonhard Euler is a Swiss mathematician, and Augustin Louis Cauchy is a French mathematician, physicist, and engineer. So they have their names on many of the things we do in this semester, and what we are doing today is set of differential equations that are named after them. They have a very simple pattern to them. So for example, let's look at this one that we are going to see very often. This is a second order version of it. You see that power of x shows up, and the power of x is equal to the number of derivatives that we have. So x to the power of 1, y prime, and so on, or x cubed, y triple prime, x to y double prime, and so on. A, B, C's are just numbers for us, and of course the leading term should be non-zero, otherwise that term would not be there. Okay, the method of solution here is going to be very straightforward, inspired by the fact that if you have a polynomial and you differentiate it every time, you lose one power. So it's as if this is compensating for how much you lost during differentiation. Let me go ahead and demonstrate like this. Suppose I have x, y is equal to x to some power. Let's call it power, say, n. If I differentiate, what happens? So n comes on front, and of course this is for n, a constant number. If you differentiate a second time, well, you lose two powers. So this becomes n times n minus 1 times x to the power of n minus 2, and so on. So if you multiply this term by x, you go back to whatever power you had, except that now there's a coefficient in front. If you take this one and multiply it by x squared, again, you are going to compensate with what you have lost, and now you have n times n minus 1 times x to the power of n. So that is the motivation before what we are going to do. We are going to say, well, let's investigate to see if this is going to be a type of solution that's going to work for us. The reason for that approach is, well, when we multiply by these powers of x's, all of the terms are going to be x to the power of n. We can factor it and see what is left, and perhaps we can manage the problem in that way. So for example, let's take this problem that we are going to look at extensively. So I have a x squared times y double prime is going to be this one. So it's going to be a n minus 1 x to the power of n, and this is going to be b times this one. So that's going to be b n x to the power of n, and this is just plain c x to the power of n. I want this to be 0 for all x's. So I factor x to the power of n. I'm left with a times n minus 1 plus b times n plus just a c equal to 0. If I want this to be true for all x's, then this parenthesis has to be 0. So a n minus 1 plus b n plus c has to be 0. What are we looking for? We're trying to figure out what exponent x, what exponent n is going to match in our problem. So when you expand this thing in terms of n, you get a n squared plus a b here and minus a here, so b minus a n plus c equal to 0. Well, Now you can go ahead and find out what n is. So it's just a quadratic equation. You apply quadratic formula and then you find your roots. As we saw previously, where any quadratic equation either has two distinct roots or two identical roots, or in case when a, b, c are real numbers, perhaps two complex conjugate roots. Almost all problems that we are going to encounter, a, b, c, are just real numbers. So our classification comes down to the following. Either you have two, n is two distinct real roots, or we have n to be two complex conjugate roots, or we have n is identical roots, or a pair of identical numbers. Can of course write the formula for it, but perhaps it's the best to go ahead and practice some straightforward examples here. So suppose I have x to y double prime minus 2xy prime minus 4y is equal to 0. So just to practice one more time, we are aiming for solutions that are of power type, and then therefore we are going to get n times n minus 1 times x to power of n minus 2 n times x to power of n minus 4 x to power of n. So when I plug it back here, that is what I get. I factor my x to power of n. From here I have n squared minus n. I have minus 2n and minus 4. So the way this thing is going to work is, in case we have n squared minus 3 and minus 4, everything's going to work out for me. I'll factor this thing, n minus 4 times n plus 1. So I'll have n is equal to 4 and n is equal to minus 1. So that one tells me that the solutions of the x to power of x to power of 4 and this one x to power of minus 1 are acceptable. So the solution is going to be any linear combination of these two. Since this is a linear equation, any linear combination of them. So ax to power of 4 plus bx to power of minus 1 is the solution of this problem. Every now and then we come across cases when we have two identical roots. So in that case we cannot just copy this thing twice and say that's a solution, because you could just factor x to the power of 4 or whatever power it is and just merge them into one solution. So what is the second solution in that case? To see an example of that, let's go ahead and so this is an example that led to two distinct roots. Here's another example. Suppose I have x squared y double prime plus say 8x y prime plus just plain y equal to 0. So our equation is going to be, as we said before, n times n minus 1 times, so there's a 1 here, plus 8, whatever coefficient I have here, and this is just 1 here, just 1 equal to 0. So this is our auxiliary equation or characteristic equation They give various names to that type of equation. And so standard way of naming things that are associated to something that we are doing, auxiliary or characteristic and such. So I have n squared. I have a typo here, so excuse me, 4x squared. So let me just put my number, 4n squared. So I have 4n squared minus 4n plus 8n plus 1 is equal to 0. So it becomes 4n squared plus 4, excuse me, 4 plus 4n plus 1. The problem, you see right away that when you factor this 2n plus 1 to 2n plus 1, both roots are going to be minus a half. So if I want to write the solution, I can write x to the power of minus a half times some constant here, and b, well, that's a big question. What is the other one? I cannot just write that a second time because it's just a copy of whatever we had. We want the two solutions to be linearly independent from each other. We didn't emphasize that concept all that much, but the two equations, the two formulas should be different from each other. So how do we go about finding the second solution? Well, this is a topic we covered before. We mentioned we had a topic that when you have one solution, how would you get the second solution? Let me just remind you, if you have x squared, excuse me, if you have an equation written in the form of, say, y double prime plus some function times y prime plus some function, known function, times y equal to 0. And one solution is given, y1 is given, or somehow we found it. So it's like y1 is given. How do we find the other one, y2? So we had a method of reduction. We can go through that process from scratch, or we had a ready-made formula for it. Y2 was y1 times a big integral where you had exponential of minus integral of p over y1 squared. Let's practice that and get ourselves a y2. So in this case, y2 is going to be whatever y1 you had, x to the power of minus 1 half times an integral of exponential of. Now, who is my p and who is my q? Standard mistake is to think that the p is just 8x and q is 1. You want to avoid that mistake. Always remember these formulas are tied to standardized form. The leading coefficient has to be made into 1 so that we don't go ahead and everybody do something different. If you had multiplied it by 2, these entries will be of course different. If you multiply by 3, these things will be still different. So to standardize, to proceed, we have to make this thing into 1. So how do I do that? Just divide by 4x squared. So you get y double prime plus 8x over 4x squared. So it's going to be 2 over x over y prime plus 1 over y prime and 1 over 4x squared y equal to 0. So this is the standard form of the same equation. So what is my p? My p is this quantity. So my p minus integral of 2 over x dx divided by, okay, denominator is y1 squared. So whatever I had here, x to power of minus half, I have to square that, and then I have to integrate the whole thing again. So let's go ahead and do it. So x to power of minus a half integral of this one, of course, this is exponential of minus 2 logarithm of x. We don't need to worry about our constant here. We could put it, but you don't need it. X to power of minus 1/2 to power of 2 is going to be, of course, x to power of minus 1, and then dx. Well, what is exponential of minus 2 logarithm of x? We have seen this issue multiple times. How to handle it? Exponential of logarithm of x to power of minus 2. So this is x to power of minus 2. So I'll have x to power of minus 1/2, 1/2 integral of this is x to power of minus 2. It's good to make a note of this thing because we come across this issue so many times. That is x to power of a. Okay, so it's just x to that power. And I have x to power of minus 1 and then dx, and then x to power of minus 1/2 times, this is x to power of minus 1. If when you simplify it, it's just 1 over x. And of course, all the way through, we are assuming x is, either we have to assume x is positive or negative. Let's just take it that x is positive so that we don't need absolute values. Or so this becomes x to power of minus 1/2, and then I have logarithm of x. And then, of course, you can have a constant. C times that would be a copy of the solution that you had. Second solution that we were looking for is x to power of minus 1/2, whatever this one was, times logarithm of x. Why didn't I bother with the c times x to power of 1/2? I could have put it there, but I already have it here. So that's just going to be merged into this and would not make a big splash or anything. So if you want to factor it, be my guess, you can factor x to the power of minus 1/2, for example, times a plus b logarithm of x. If you want to still rewrite, so these are just various ways of writing the answer. These are all same thing. Okay, so what we saw is, in this case, the roots were identical. We had to make use of formula we developed under reduction of order a couple of sections ago. Reduction of order, that's where it comes up. Okay, so let's go back here and see what happens. So we have an equation. We noticed that when you have a monomial power of x, when you differentiate it, every time you differentiate, you lose one power. The Cauchy Euler equations are always nice in that the power of x in front of our term is matching the number of derivatives. So as many powers as you lose, that's what you gain and compensate, and you're whole again. All that happens is that you get some factors depending on your exponents. These factors and the coefficients together form an equation. Linear, it's going to be linear, quadratic, or cubic, and so on. Sorry, my screen is sensitive to the stylus. we practiced this problem for quadratic, but of course you can do it for cubic and so on. Your degrees just goes up, and the equation that you have to solve becomes a bit more complicated. We are saying that when you are solving this quadratic equation, three scenarios show up. Either you have two distinct real roots, that's what we did first time around here, that's the most straightforward, or you have identical roots. So we did the identical roots. We had to use reduction of order to get the second solution, and typically a logarithm is involved there. So you always see some logarithm resulting from this integration. Third possibility is, what if you have complex roots? When you solve a quadratic equation, that's a possibility, and we want to observe that situation. So here's an example. Example which leads to complex roots. Now, when we start with real numbers, we always end up with complex conjugate roots. The two roots, one is positive, one is negative. But at any rate, suppose we are asked to solve, say, 4x squared y double prime plus 17y equal to 0. So let's take it and run just like we did before. So it's going to be 4n times n minus 1 plus 17 equal to 0. There was no middle term here, so I don't have anything here either. So 4n squared minus 4n plus 17 equal to 0. Now we look at that and notice that we doesn't factor. I mean, that can happen in other cases as well. Like if you have two distinct roots, there's no guarantee that they always have to be nice numbers. It could be any radical numbers or something. So in this case, we are going to have n is 4 plus or minus 4 squared minus 4 times the first and the last numbers divided by twice the first number. So n is 4 plus or minus. So 4, I factor 4 squared. So I'm multiplying, I factor it. Then I'll have 1 minus 17 divided by 8. So n is equal to 4 plus or minus. Square root of that is a 4. Square root of minus 16, that is 4i divided by 8. So I'm getting the two roots. 4 over 8 is 1/2. 16 over 8 is 2. So what is my solution? This is just like the very first problem we did. A times x. The power of x is that funny number, 2 plus 1/2 plus 2i. And the other one, x 1/2 minus 2i. These are my exponents. If you are comfortable with complex exponents, that is good enough. However, most often you are being asked to convert it to the real form. So the idea is to write it in, what is this thing in real form? Real form means, well, even if there is a complex number, it's hidden. It's not part of your function component. So for real form, we need, again, it's the name of Euler here, that Euler's formula, cosine of theta plus I sine of theta. Well, That is good so far as your base is e. What here is my base is some arbitrary number x. What do I do? So I need to modify this. Remember from the topic we just mentioned, exponential of logarithm of x, we know is just x. Is that right? That's basically from pre-calculus. So I can write x as exponential of, so if I have, suppose I want to figure out what is x to the power of I theta. Instead of x, I write exponential of logarithm of x, and the whole thing to power of I theta. So it becomes exponential of I times theta logarithm of x. Now this Euler form says that if you have, if whatever, let me convert it to something colored, that so whatever you have here, let's make it into a box. That is what is showing up on the right hand side. So the box now contains this. Whatever it is, I just copy it through. I don't need to be worried about the complexity of it. Euler formula really says e to power of I box is equal to cosine of box plus I sine of the box. So my box happens to be this. So I'll have cosine of theta logarithm of x plus I sine of theta logarithm of x. Let's practice. If I have x to power of 1/2 plus 2i, what do I do? X to power of 1/2 is not objectionable to me. I know what that's square root of x. I'm multiplying it with x to power of 2i. So x to power of 1/2 times x to power of 2i, let's write it, is e to power of logarithm of x to power of 2i. So x to power of 1/2 e to the power of I times 2 logarithm of x. So now I open this, apply the Euler's formula to this. I'll have cosine of 2 logarithm of x plus I times sine of 2 logarithm of x. Now one nice thing about complex conjugates in setting that everything else is a real number is that the solutions, everything comes in pairs, one with plus I, one is minus I. So I could redo all of this thing from scratch, but here is a shortcut. If you have one formula with plus I, then you are going to have another formula with minus I. So what was our solution? Our solution was a times this and b times that. Can you guess what's going to happen? If I take this, multiply by a, take this one, multiply by b, let's go ahead and do it. So I have, my solution is going to be a times one of them, so x to the power of 1/2 cosine of 2 logarithm of x plus I sine of 2 logarithm of x, and b times cosine of 2 logarithm of x minus I. Made a mistake here after all that. Sorry, lecture. The idea was when you start with minus, you get a minus here. So I forgot that, sorry for that. Minus I times sine of 2 logarithm of x. And I forgot one more thing, x to the power of 1/2 here. So I can factor my x to the power of 1/2. I have a cosine and b cosine, so it's going to be a plus b cosine of 2 logarithm of x. And the other one is ai minus bi, then sine of 2 logarithm of x. Now whatever a and b happen to be, this thing is going to be some constant. We might as well call it, say, m. Whatever a and b happen to be, I is also some constant. This whole thing can be brushed under carpet and say called n, just to reduce the clutter in the look of our solution. So y becomes x to the power of 1/2 some number times cosine of 2 logarithm of x, some other number. This could be complex if you want. It could be real. Usually they are real. Sine of 2 logarithm of x, and then that is the solution. So what you see in cases where you have complex conjugate roots is some power of x times sine and cosine of logarithm. Same story happens when you go up to third order or fourth order equation. We just have more pieces, but other than that, it's all same familiar. Now, once again, notice that for logarithm to make sense and for the square root to make sense, of course, x has to be positive. If your x wants to be negative, then you can make a change of variable or something to get rid of that negative sign. It's also possible to change your equation to ordinary second order with constant coefficient with the change of variable. So that's one topic that you can see. And another fact is that you can have your expansions, instead of being based on just x, it could be x minus some central value. In that case, the process just goes through exactly the same way, and you get similar results. Okay, so let's go back and take a look what happened here. We have Cauchy Euler equations. Characteristic form of this thing is the power of x matches the number of derivatives taken from y. That gives us the idea to start with a monomial of this type. When you differentiate, some factors come in, and that leads to equation. It's a polynomial equation, so we solve it. We face the obstacles of polynomial equations, and then if you have distinct roots, that's the easiest one. You just already are done. If you have real distinct, this problem is straightforward. Complex conjugates, we have to apply Euler formula to convert it to real form, and if happens to be identical, that's the slightly more complicated version of the problem, where we have to apply the reduction of order method to get the second solution or other solutions, and then we'll be done. Okay, so we are taking care of one more topic here. Until next time, good luck and God bless.